Well, hello and welcome to our NVIDIA GTC21 presentation. My name is Peter Blaser. I'm a Vice President here at CPFD Software. I'm going to begin our talk by introducing you to our product, which is enabling a variety of technologies that are literally changing our planet for the better. And we're going to look at the impact of GPU acceleration on not just our products, but our clients. And we'll zoom in and do that with a case study looking at one particular client that has a unique and novel waste to fuels technology and what GPU and multi-GPU simulation is doing for them. Then I'm going to turn it over to my colleague Andrew Larson. Andrew is our lead software engineer, GPU specialist. He's going to pull back the curtain, so to speak, and look at specifically what we've done, the road we've gone down in terms of GPU parallelization, some exciting things that are happening right now, a product that's imminent for release and our testing results, and where we're going with all this over the next 12 months or so. And then we'll wrap up by looking at the impact of all this on the multiple industries in which we work and really a shift that we're seeing in those industries to more sustainability and renewables and clean technology. So thanks so much for joining us, and let's get started. So first, let me introduce our company. Here at CPFD Software, we have specialty expertise in fluid particle systems and simulation of those systems. We work in a variety of industries, from traditional ones such as refining, petrochemicals, power generation, materials, chemicals, and so forth, and a lot of exciting clean technologies, renewables, gasifications, and so forth. Our expertise is codified in a product, a software product named Barracuda Virtual Reactor. Virtual Reactor models the gas particle hydrodynamics, thermal behavior, and chemical reactions in industrial units. This is award-winning software technology. We have received multiple highly commended designations from the International Chemical Engineering Society, the ICHEME, and most recently won Hydrocarbon Processing's Best Software Technology in the 2020 HP Awards. And the way it's used is to assess performance through simulation. Like most simulation technologies, it can be used to determine the root cause of the underlying phenomena behind what's happening. But what's really exciting here is this is doing so in units that are typically running 24/7, often for years on end. And so making changes can be extremely costly, and we reduce the risk of those changes through virtual testing. Invariably, what happens is we identify additional optimization opportunities, and ultimately, this enables our clients to do rapid, informed, scale-up technology development, IP protection with confidence. So, how does simulation speed affect our clients? We're going to talk about speed up. Conventional wisdom, and it's certainly true, is that accelerated simulations, and in our case, GPU accelerated simulations, take less time to complete. Absolutely true. So consider 100x speed up, and we're going to show that and more. What does that mean? Well, it means a month-long simulation's done in 8 hours. A week-long simulation's done in 2 hours, and a day-long simulation takes 15 minutes. And that's certainly true. But practically speaking, with our clients, we've observed something else. Really, a practical outcome that we've observed is that the GPU accelerated simulations are really making the impossible possible. And to illustrate this, we're going to dig into a case study. This is with a client company of ours, ThermoChem Recovery International USA. We're going to call them TRI for short. They're doing some super exciting things. They have a technology that converts trash, literally municipal solid waste, into jet fuel. And we're going to explore their digitalization journey, which has really been enabled by our GPU acceleration. Well, let me introduce TRI to you. TRI creates technology that produces green renewable fuels and chemicals from a variety of feedstocks. Here at the bottom, I'm showing various biomass sources. At the top, we have waste that would otherwise be sitting in a landfill. And TRI's technology, I'd say, is marked by two things, characteristics. One is very high feedstock flexibility, which enables the use of the lowest cost feedstock, not just in terms of dollars, but especially considering the overall environmental footprint when you consider things like transporting the feedstock to the biorefinery. It's also marked by a very high carbon conversion and efficiency. So really, their mission is sustainable economics with minimum overall environmental impact. And it works. Here are samples of various fuels and other products created using their process, their technology. We have jet fuel, diesel, various waxy products that were created using the woody residuals, as well as municipal solid waste or MSW feedstocks. And these are drop-in fuels for strategic domestic markets. At the heart of TRI's technology is a two-stage gasification system. So bear with me for a second. I'm going to get a little engineering on you. Some of you are going to care about the details. For the rest of you, just know this is what our specialty software simulates. On the left, I'm showing a deep bed. Actually, there's two fluidized beds, two deep beds here. On the left is the steam reformer. It is indirectly heated by a proprietary, unique pulse combustion system. And on the right is a carbon trim cell. And this sits in an overall biorefinery process. The entire thing has been demonstrated at a process demonstration unit, or PDU, I'll call it later in this talk, in North Carolina, including all components, the feed system, the steam reformer and the carbon trim cell, various gas chromatography units, GCUs, and a Fischer-Tropsch synthesis unit. So how do you take a unique idea and commercialize it? What are the complexities involved here that would benefit not only from digitalization, but from GPU acceleration of that digitalization? At the heart of the technology process development here is a digital syngas model. It takes everything from the unit operating conditions, what's the geometry and what are the flow rates through it, and temperatures and pressures and so forth, as well as the feedstock properties. If you're putting wood chips or municipal solid waste into this steam reformer, it'll behave differently. Put that into the syngas model to predict the types of things coming out. What is the syngas composition and flow rate? What's the carbon conversion, the gasification efficiency, and other important engineering parameters? And as we dug into this, we realized there's a lot of things feeding into this model. It's not 1D, it's 3D, it's multi-phase. And so you have the gas particle hydrodynamics. And it's not just one type of particle. There's bed particles and feed particles, all with different sizes and size distributions and densities and other material properties. And then there's the evolution of that over time. There's the drying and decomposition, and then the chemical reactions that are happening. How's the thermal changing? What's the transport phenomena? So it's a great idea to have such a digital syngas model, but how do you create it? Well, let's start by looking at how engineering is done in the first place here. So typically what would happen, and certainly this was part of it, necessary, not sufficient in this case, is a systemic scale-up. So you start with small-scale tests, a cold flow unit to determine things like fluidization behavior of particles. Then you scale that up in terms of the complexity of the chemical reactions and the heat. So a feedstock test reformer, very small unit, 2.5 kilograms an hour. If I put feedstock A in, what am I getting out? How does it behave? Then scaling that up to a process demonstration unit that I showed you on the last slide, 4 dry tons per day. And that's a lot smaller than a commercial unit, which could be 300 dry tons per day or much larger. And so what we did here is we took the existing process and augmented it through digitalization. But it wasn't just digitalization. Here we experienced true digital transformation. So give me just a moment to talk about something, a buzzword maybe we're hearing a lot about today. Digital transformation is not just using digitalization technologies in an existing process. Simulating a unit before it's built has been done for a long time, and that is not truly transformative in and of itself. In fact, neither is running a process demonstration unit before running the commercial unit. It's a step better. Rather, digital transformation occurs when you augment and change the existing processes themselves through the digital technology. So here, we didn't just take it from concept through to small scale tests to process demonstration to large scale commercial. But the flow of information worked both ways. In some cases, we got to a point on one of the larger scales and said, we'd like to augment this model further. And the very experiments that were built were different as a result of using Barracuda and using the GPU accelerated version in this work. Let me illustrate that a slightly different way. So here is your traditional engineering scale up. So as you go down in this list, you're going up in complexity from the cold flow and characterization tests to the feedstock test reformer to the larger scale process demonstration unit to commercial. And this is the traditional information flow in traditional engineering. So here's an example. On the right, I have a graph showing some outputs from the system in terms of the CO and H2 gas compositions under two different conditions. Those will remain proprietary here. We have the test data at the FTR level on the left. Hey, the two conditions behave differently. Can we predict that? Yes, we can predict it. So in the middle, I'm showing the prediction at that level. So the model's good at that scale. Then we move up to the PDU, the process demonstration unit. And we're able to predict that. Then we validate against that and move up. That's traditional workflow in terms of engineering, and it's the traditional process used even with the digitalization. But here, the same fully integrated validated model was used whether it was moving up in complexity or realizing we have a missing piece of information in one of those submodels. Let's go back and build a new test, creating a truly digitally transformative process and a model that is holistic throughout. So let me show you a few results. This is at the PDU level. These are all different views in the exact same simulation. On the left three views, I'm showing the particles. Not all the particles, but digitally we can remove some of them from the view so we could see how the freshly injected feed is moving through the system, the evolution of the biomass and char content, the moisture in those particles, and now all that affects the evolution of the gas species on the right. These are some of the gas species in the digital syngas model. Even at this scale, highly dynamic, you could see the lateral effects of mixing, which will become much more important, which became much more important as we moved to commercial scale. So then at commercial scale, here's an example on the right of a much larger unit. The hydrodynamics, the gas bubbling behavior, how the lateral mixing is handled is typified by the animation I'm showing at the right. These were run at various different feedstocks. Black liquor, which is a byproduct of the pulp and paper industry. Forest residuals, your biomass. The municipal solid waste. And they're also run at different scales. Recent commercial designs have been simulated at 500, 1,000, 2,000 dry tons per day feedstock throughput. And looking at not just the hydrodynamics and mixing, but the overall prediction of process performance, the outlet gas composition. And in terms of a project update, the most recent iteration of this is Project Sierra. This is a project by Fulcrum Bioenergy, just outside Reno, Nevada. This is a 500 ton per day facility, and the sustainability of this one's actually quite cool. It takes you municipal solid waste and is converting it to jet fuel. And the sustainability is really not just in the technology itself, but the close upstream and downstream integration. So it's close to one of the largest landfills in the United States, and the supply chain is integrated upstream and downstream. So obtaining the waste from waste management, uh, offloading the product, the fuel, to Marathon Petroleum, the variety of airlines, the U.S. Navy and Air Force. And this is a snapshot of work in progress. The digital transformation is ongoing here. There's software and technology improvements, and my colleague Andrew is going to speak about that in just a moment in terms of the speed up we've seen, are seeing, and will see soon based on what we're doing. We're going to talk about that. And beyond just the speed aspect, there's other aspects we're exploring in our R&D, whether it's involving AI, big data, machine learning. Is this one going to go to real-time process control? So lots of exciting things happening. And lastly, I got to say, this isn't just a one-way, one company project. We talked a little bit here about what TRI and CPFD and how we collaborated in this process, but it's much larger. We work closely with NVIDIA on not just the GPU acceleration, looking forward to running on a whole series of DGXs we're acquiring now for our in-house and our data center usage. And then for overflow and quickly trying out the latest technology, we run on the cloud, powered by AWS. So with that, I'm going to turn it over to my colleague Andrew. I've talked a little bit about what this project's about, and now he's going to pull back the curtain and talk about how really this has become possible through GPU acceleration. Andrew, over to you.
Yes, hello. My name is Andrew Larson. I'm a lead software engineer here at CPFD Software, and I specialize in GPU acceleration. Specifically, we use the CUDA framework to accelerate our computer-aided engineering software. Yeah, thanks for that introduction, Peter. I mean, Peter is talking a lot about why we should care, what engineers are doing with our software, you know, the industrial scale and the nature of the problems that we're trying to solve. And so what I'd like to do is kind of take a step lower and talk a little bit more about the technical details in terms of what's in our solver and the problem we're talking about concerning, you know, the acceleration and, you know, what's the challenges that we're facing when we're accelerating this code. And so, you know, we're trying to take a step back here and look at, you know, where were we in 2009, and then, you know, 10 years from now, and then, you know, we'll look a little bit further into the future here. But to appreciate kind of what we're working on, we can talk through where the code has been. And so in 2009, when we're talking about doing one simulation second per day, this was on a serial code run on a single CPU core, you know, with the clock speeds that were available at the time. You know, and just in the brief here, we can see that there's a big change in the last 10 years, and we're able to simulate 68 simulation seconds a day. And so that's a huge difference for the engineers that are trying to solve these hard problems. And how we got there is through this process of applying acceleration. Okay, and then we used the NVIDIA CUDA toolkit to do that. And the aspects of the solver that we had to deal with are, you know, there's several different areas here. And so we have the Lagrangian discrete particles, which are usually very easy to accelerate. We have the interpolation, where we're taking these discrete particles and we need to aggregate their values down onto an Eulerian grid. We have these particles that need to interact with the geometry. When they hit walls, they need to bounce correctly, they need to bounce multiple times. We have particles going into the system, we have particles going out of the system. And then we also have areas where We have particle-particle interactions where particles can't flow into the area of the vessel because there's already particles there. We have the Eulerian side with the linear solver, where we have multiple fluid species, or we have energy calculations, or we have the pressure calculation, where we have to calculate all these properties, and they're all on the Eulerian grid. And so we use that linear solver there, and that's one component that we have to deal with. And then there's chemistry. And so Barracuda Virtual Reactor is able to do chemical reactions, and these then are often, the time scale is much different than the hydrodynamic time scale we're looking at. And so we have another set of solvers and calculation that we have to deal with. And so what ends up happening in our code is that we actually have a fairly flat profile where any one of these things is not enough to result in acceleration for the rest of the code, right? We can't go do the linear solver, put it on the GPU, and then we're done. It doesn't work that way. And so we have to look at all of these pieces, and we'll see some of that in the next slide when we talk through the various improvements and how we got to 68 simulation seconds a day per 2019. And then of course there's also, we did accelerate things, and that was a long-term effort, many years that I worked on it. But in that time period, we've also got better hardware. CPUs are faster, GPUs are faster, hard drives are faster, everything's faster. For the other piece then, of course, right, we're looking at the code. It was serial. We got to parallelize it. And then coming out of that, there's just general code improvements that have also resulted where, when you have to start to make things concurrent, things get separated, things get put back together, slices get made where parts are separated, and there's usually some sort of efficiency that's gained as a part of that process. Okay, and so, moving for this particular case study from TRI, we're looking at what was happening in 2009. We were getting 1 simulation second a day on a single CPU with Barracuda Virtual Reactor version 14. And then as we move through time, right, just in CPU hardware improvements, it goes to 2 simulation seconds a day and version 15. As we then go and we add these different areas of GPU acceleration, right? The first, we're looking at, oh, well, we did the linear solver, and we're getting 10 seconds a day with version 16. And then we move to, we're parallelizing all the particle operations and most of the fluid calculations. And as we add more acceleration to more parts of the code, right, we have to work our way through this flat profile. With version 17.3, we are seeing even more gains where we're getting 29 seconds a day. At that point in time, then we're moving on, years later, where the bottleneck that is coming up then is chemistry. And the first step we did there was to actually parallelize it on the CPU side with OpenMP, and we got gains. And then we took it a step further with version 17.4, where we actually put the chemistry then on the GPU and got even more speed up. And so, through that 10 years where we're having hardware improvement and we're consistently working our way through the code, taking what was simply serial and pushing it over to parallel, and having to address, not just a linear solver, but how do we do interpolation? How do we do chemistry? How do we do, each separate piece and accelerate it? We're able to move from 1 second a day to 68 seconds a day in 2019. And now, these engineers, they have something where they can work with these problems and get the feedback they need to avoid pitfalls or explore a space that they couldn't explore otherwise, because they can actually get that feedback. And simulation is a way that they can do that. These units are so big, they can't afford to run experiments, both in time and then in just the amount of money it would cost to try to build something like this. So that's 2019, and it's now 2021, and so there's another 2 years here, and I've been spending a lot of my time then working on adding multi-GPU acceleration to the solver. And so here, 2021, I wanted to give you a little taste of kind of the size of the problems that we're working with, or the type of problems. So we're looking at a circulating fluidized bed combustor. We're looking at fluidized catalytic cracking regenerators. And when we're doing these simulations, we want to scale the problem for you here. We're talking about 10 to 20 million discrete particles that we're running in one of these calculations, and cell counts that range from 100,000 to 800,000. And of course, we can do more. And so that kind of frames up, what are the challenges in the code and what are the size of the problems we're running. And now we have, our 2009 runs at 68 seconds per day. And now we're looking at what did we do in the last 2 years where we're adding multi-GPU acceleration to our code, and what sort of speedups are we getting? And so if we're looking at just improving the code, and we used CUDA managed memory to do this, and we're looking at adding, a single GV100 and changing it to 2. We're using newer hardware. We're moving from Pascal to Volta. We're adding a third GPU. And then there's also all this other hardware improvement that's happened in the last 2 years. And if we add up all these, we're looking at an increase in simulation speed where we're going from 68 seconds a day to 608 seconds a day. And so if we look at this progression, right, here's another chart, 68, 94, 209. And as we add, the optimizations in the code, the ability to add multiple GPUs, and the hardware improvements, again, we're able to take this huge step up from just 2 years ago where, we see something with the 17 series of 68 seconds a day. And now with our version 21 that will be coming out, very soon, later this year, we're looking at something that's 600 simulation seconds a day. And so again, this changes what these engineers would be able to do and look at and explore in terms of their space to improve these industrial scale systems so that they're running correctly, emissions are lower, and so on. Okay, and so that's where we're going to be this year. And of course, we're not going to stop there. There's still plenty of work to do. And so looking forward, we can say, in the next year, we're looking at doing other improvements. And so, top of the list here is currently our linear solver is still restricted to a single GPU. That'll be one of the first things we address. We expect to get about 10%. We're going to reduce memory transfers another 5%. This together and other small fixes are going to provide us better scaling from 2 to 3 GPUs. We have, again, new hardware to look at with the Ampere series NVIDIA GPUs. And you put all this together and you take out some of the bottlenecks, we'd expect to see better scaling from each GPU that's added, where typically we're able to get maybe 1.5x now. And as we move forward, the scaling is going to get better as we remove bottlenecks and fix the areas where the code is not efficient. And so again, we were at 1 second a day 12 years ago. We were at 68 seconds 2 years ago. We're at 600 seconds today. And now if we take these further improvements, we're doing another 2x improvement here where we put on the linear solver, we fix things up, we get better scaling, we get new hardware, we add another GPU, and we could be looking at running 1,500 seconds a day next year. And it really opens up what is possible, right? We're able to take these month-long simulations and bring them down to an hour maybe. And then what happens, right, is it really enables these process engineers or, these people that are trying to design these very complicated industrial systems to be able to iterate maybe on a daily basis and explore the design space or the problem space much more quickly. And so this is really, right, like, a lot of what you see is like, okay, we're making, we use GPUs and multiple GPUs, and it's this much faster for this algorithm, and then it's this much faster in this case. Okay, well, here we're trying to take a step back and look at what is happening in the last 10 years, in the last 12 years, that has really changed what we're able to do kind of more collectively or out, in the application area, and enable people to really be able to look at this stuff, more virtually, right? We're able to simulate it, and we're able to simulate it very quickly, so we can get that information we need to make good decisions. All right. Well, now turn it back to you, Peter.
Well, thanks, Andrew. The speed's incredible, and we see it impacting all the industries that we serve. But more than that, we're seeing a shift, and really it's enabling newer sustainability technologies and applications that previously have been intractable. This is possible by our own investment into R&D, and also by a lot of the awesome technologies put out by NVIDIA. Year after year, I'm amazed at the speed ups we're seeing, and able to take advantage of by working together. So, in terms of what we're looking at with the sustainability applications, we went through the one case study, the waste to fuels through TRI. There's a lot of other things going on: waste to energy, waste to chemicals, biofuels applications. Here's a really cool one. If you've not looked into the circular economy of plastics, look up terms like advanced recycling or chemical recycling. This is not just traditional recycling. So traditional recycling is essentially melting and extruding plastics and using it again a few times. The challenges there are the product quality degrades fairly quickly, and the impurities really make much of the recyclable plastics you throw in the bin don't actually get recycled because they're too contaminated. With advanced recycling or chemical recycling, these plastics are ground up and used as a feedstock right back into a reactor, making the basic molecules and rebuilding the plastics in the first place, which allows for an infinite recycling loop, much more broadly able to handle a wide range of impurities. And other decarbonization applications in the energy space: chemical looping combustion, carbon capture materials. Here's some quick examples. We're working on polysilicon reactors. Many of those use multiple fluidized bed processes to make the very raw materials that from which the solar panels are built. And we have multiple companies working to reduce their carbon footprint in cement production. So lots going on. Love to tell you more. Contact us. Love to talk it through with you. So in summary, what we're seeing with Barracuda Virtual Reactor on NVIDIA GPU technology is that problems that were previously not possible to solve are now solved regularly in industrially relevant timescales, and this enables sustainability technologies that are changing our planet for the better. There's a bunch of information here. When you get the handouts, you can click on the links about what we are doing with TRI, about Project Sierra, Fulcrum Biofuels, about some of the awards and what some of our customers in other spaces are doing. And if you have any questions, please contact us. Be sure to follow us on LinkedIn and stay in touch. Thanks so much for taking the time to view this.